Hey guys, here's a short video about conservation of momentum. This is to explain why it happens. So last time you guys did the air track simulation, and the idea of that was to help you see that conservation momentum really is a thing. So we saw in that when we measure the momentum of two pucks before they run into each other, they have the same total momentum as they do after they run into each other. So the momentums change. One gains momentum, but it's always by the same amount that the other one loses momentum. So the total momentum is conserved. The total momentum is always the same. You saw that was true last time. And this time I want to show you why that actually is the case. So we're just going to demonstrate why it turns out this way. Now, you already have all the knowledge you need. You have all the pieces. I just need to point them out to you and how they work out. So let's imagine here a cannon firing a ball. Let's put me right here. That looks like a good place for me. Okay, cannon fires a ball. Now, we studied Newton's third law. So we know that the force that is acting on the ball, pushing it out of the cannon, is the same as the force acting on the cannon, which is pushing the cannon backwards. Now, in reality, there's expanding gases in there. When we light the gunpowder on fire, it turns into a gas, and that's what pushes the things apart. But for our purposes, we can simplify that and say that the ball is pushing on the cannon, and the cannon is pushing on the ball. That's what the third law says. How hard my finger is pushing on my hand, that's how hard my hand is pushing on my finger. Third law. So the force on the cannon is the same as the force on the ball. Now we're going to assume as we fire this thing that it is going to be traveling down the barrel for 1 second, which is obviously not realistic. A cannonball doesn't spend anywhere near that much time in the barrel. But just to make the math easy, we're going to say it is. And we want to figure out how fast the ball is moving when it leaves the barrel. Step on the path here. Okay, so we're going to assume that there's a force of 1,000 newtons, and that 1,000 newtons is pushing on the cannon and it is pushing on the ball, and that force lasts for 1 second. Okay, and again, we want to figure out how fast the ball is moving as it leaves the barrel. Now to do this, hint, 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 you want to use the impulse equation. This is the one that we had before. Now at this point, I want you to pause the video and see if you can figure this out. Figure out what the speed of the ball is after it leaves the barrel. Okay? Okay, so I'm going to assume you've come back now and you're either stuck or you've got an answer. So I'll see if I can get you unstuck if you are stuck here. Okay, so the force is given. That's 1,000 newtons. So that's 1,000. The time is 1 second. So we have 1,000 times 1. So the impulse, the force times time, that is 1,000 units. And that is equal to the mass times the change in velocity. And the mass of the ball is 2 kilograms. So we have 1,000 on this side and 2 times the change in velocity on that side. And then you do the algebra to solve for the velocity. Okay, pause it if you want to just get unstuck. All right, now the answer is, as you probably figured out, 500 meters per second. Okay, 1,000 divided by 2 is going to be 500. So the change in speed of the ball is 500 meters per second. It went from 0 to 500 as it traveled down the barrel, and that's the speed of the ball. Great. Okay, now let's find the speed of the cannon, because the cannon is being pushed back the other way. Same deal, 1,000 newtons, 1 second in the barrel. We're still going to use the same equation here. So pause it till you have an answer. But we use the same technique as before. Okay, welcome back. And the answer is -1 meter per second. Now, you might not have gotten the minus sign, and that's okay if you didn't, because I think you understand that the cannon is going to the left. The ball was thrown to the right, the cannon is going to the left. So if we call to the right the positive direction, then that means that the cannon is going in the negative direction, and that's where the negative comes from. Now, it's also just as valid to say, well, the ball was going to the right and the cannon's going to the left. And this negative sign just represents it's going to the left. What I'm mostly worried about here is that you recognize it's going the opposite way and it's going 1 meter per second. All right, that's great. So we got 500 meters per second for the ball, 1 meter per second for the cannon, and in the opposite direction. So now I want you to calculate the momentum of the cannon and the momentum of the ball. Remember, the ball is going 500, the cannon is going -1. Pause it again, come up with the momentum for each of those objects. And if you can't remember, P equals mv, that's our equation for momentum. The momentum of an object is its mass times its velocity. We have the velocities here, we have the masses up here. So pause it for a moment. Welcome back. And the answers that we get are 1,000 kilogram meters per second, 1,000 units of momentum for the ball, and -1,000 for the cannon. Okay, 1,000 for the ball, -1,000 for the cannon. Now, I had you run through all the numbers and do the math yourself so that you know I wasn't just picking some weird example and making up numbers to make it look good. It actually works out this way. And if you think about it, you see it has to work out this way. What we see is that the momentum of the ball is equal to the momentum of the cannon, but in the opposite direction. And more significantly, the total momentum of the system has not changed. So before we fired the cannon, it was just sitting there. The cannon, 1,000 kilograms, the ball, 2 kilograms, just sitting there, not moving. So the momentum of the cannon and the ball before we fired it was 0. Then we fire the cannon. We see that we have the same momentum traveling in opposite directions. So again, when we add them up, it adds up to 0. The momentum of this system has been conserved. And the reason it has to be conserved is back to the impulse equation. Anytime, the only way you can change the momentum of something is to apply a force for some period of time. And the third law says that whatever the force is, it acts on two objects in opposite directions. And that force, whatever it is, has to act for the same amount of time. Because when one object is pushing on the other object is pushing back. And when they stop pushing, they both stop pushing. So the length of time that the force lasts is the same for both. The time is the same and the force is the same, so the change in momentum is the same. But it's in opposite directions, so the total amount of momentum never changes. That's where it comes from. All right, thank you for your time. We will see you next time.